purify the water of the tunnel construction site on a highly efficient basis. It's actually a good example of successful nature conservation, but later when building the tunnel, the conditions deep in the mountain were extremely difficult, greatly complicating the tunnel construction project in every way imaginable. That's what this film is about. The project, SPB's Ritom hydropower station, built more than 100 years ago, is to be expanded and have its output quadrupled in order to improve the power supply to the Gotthard rail line. The pressure line to Largo Ritom, which is around 800 meters higher, was routed partially above ground, but must be relocated completely underground as it's being greatly enlarged. But the 3 exploratory bores on the tunnel axis made in advance showed that the rock is tricky to deal with down to a depth of around 200 meters and is crisscrossed by porous strata that are also aquiferous in part, so conditions are pretty bad for tunnel construction. So the first step is to build a gallery into deeper regions of rock that are presumably easier to work with. Only here is the sloped shaft to begin rising to the lake level. To remain as deep as possible, the shaft is also being built with an inflection in its route, as well as 2 different slopes. The shaft has a diameter of 3.2 meters. It will be excavated using a tunnel boring machine that Marty and manufacturer Heron Connect developed especially for this project. The difficult rock and the slope of nearly 45 degrees present extreme challenges, but more on that later. The sloped shaft is roughly 1,400 meters long and ends in an arrival cavern created in advance, known as the slide chamber. From here, the headwater gallery will lead into the lake. Work on the project begins in January 2019 with construction of the lower pressure gallery. After blasting, loose rock is broken off and the tunnel profile is excavated. The tunnel is lined with shotcrete and reinforced with steel arches where necessary. The gallery is used to cross the aquiferous rock strata, and as the driving operations progress, ice-cold alpine water becomes a constant companion for the miners. About 250 blasting stages are planned, with more than 20,000 holes for explosive charges. Working under these conditions is an extreme challenge for the body as well as the will to persevere. Danger is not posed by the water because the water entering the construction site is only under low pressure, and the special explosive charges perform perfectly even under wet conditions. The tunnelers on their way to work also hoped that after about 400 meters of driving operations they would pass through the fissured and aquiferous rock area and reach rock that was largely dry as per the geologist's forecast. However, it was here that enormous problems arose. After another blast, there was a strong ingress of water under high pressure of 10 bar, corresponding to a water column of 100 meters in height. Under such conditions, it would be irresponsible to venture further into unknown rock. For this reason, an exploratory bore was drilled by Marty's subsidiary Stump BDE, which specializes in geologically deep drilling. During retraction of the drill string to recover the cores, water repeatedly entered the borehole at flow rates of up to 100 liters per second. Not a good sign. After the Marty geologists evaluated the drill cores of the exploratory bore and of 5 unsuccessfully drilled drainage boreholes, it became clear. Contrary to the original forecast, some of the rock they were dealing with was highly fragmented, as well as quite aquiferous in part. This jeopardized the continuation of construction, as well as the entire project. It was clear to Marty that to continue construction, it would be necessary to use injection shields to seal the area. This process involves injection material being injected through boreholes to seal the aquiferous fissures. First, to protect the existing structure, the last 10 meters of the gallery were backfilled with a concrete plug, and the last tunnel section was sealed. The concrete plug prevented the injection material that was pressed into the boreholes from leaking into the tunnel. Under the protection of the previously created shield, the plug was then broken up again. Now, 20-meter injection shields were created on a periodic basis, followed by the excavation of 15-meter tunnels. Due to with the substantial flows of water in the rock, which according to conventional wisdom is close to impossible to stop, a hybrid injection of conventional cement and a pure resin developed by Marty's subsidiary Renasco was used. Each injection began with cement. If rock areas with relatively small aquiferous fractures and minor flow are injected, cement injections are adequate, as very little cement is washed out. After the borehole is backfilled, the pressure in the hole increases. The cement penetrates the fissures also against the water pressure and closes the fissure system around the hole. However, if rock areas with large fissures and a major water flow are injected, the cement is largely washed away. The pressure in the borehole does not increase and no injection takes place. That's why pure resin was automatically added to the cement if the pressure did not increase or was too low. The now greatly increased viscosity of the material did not allow for penetration into fine fissures, but washing out of the injected medium was prevented, leading to clogging of the large fissures. When the resulting pressure increase occurred, the system was switched back to pure cement. As in the conventional process, the fine fissures were also largely sealed in this way. That's the theory, at least. In practice, each new injection bore leads to aquiferous rock areas, and attaching the hoses for the injections is not a task for people who don't like water. However, the tunneler's perseverance and the innovative injection process developed by Marty paid off. To the astonishment of the experts, it was possible to make it through the largely aquiferous and fractured stratum after construction of 14 injection shields with nearly 1,000 injection bores. They were then able to reach good rock, as the exploratory drilling had already demonstrated. In February 2021, the shaft base cavern was built with a delay of nearly a year, and construction of the launch ramp for the tunnel boring machine could begin. The ramp guides the machine to the previously drilled start of the shaft and maneuvers it to the initial slope of 26 degrees. Then the 80-meter-long cavern is ready, and assembly of the tunnel boring machine, TBM for short, can begin. The machine is delivered in 6 separate transports. The drill head of the TBM has the largest diameter, of course, and the access gallery is precisely dimensioned to accommodate it. Incidentally, it's not an easy job for the truck driver. The drill head is lifted from the low platform loader using special hydraulics. The machine is 100 meters long when assembled. To make room for additional deliveries, it slides its way up the launch ramp during assembly. Then the time has finally come. Driving operations begin while other components are still being attached to the TBM. While the drill head has already begun to operate, the end of the TBM continues to be assembled in the launch cavern, blocking subsequent installations. Provisional solutions are required for removal of the excavated material and to supply the machine. The machine is completely in the rock after 3 weeks of interim solutions that are constantly changing in the cavern, and regular driving operations begin. During drilling, the machine's 23 roller cutters roll over the rock under high pressure, raking chips out of the rock. The loosened material falls into the cutting wheel and then into a material channel. The material slides down the sloped chute by itself, facilitated by the addition of water in the cutting wheel. The required water, which comes from the point of water ingress into the access gallery, was previously used to cool the units of the TBM. Depending on the situation, a wide array of clarifications as well as ancillary and additional work take place in the drill head during driving operations. More on that later. Let's first discuss how the machine works. During drilling, 4 driving presses force the cutting wheel up against the rock with up to 500 tons of pressure, more than the weight of the entire tunnel boring machine. The gripper shield absorbs the forces and uses its 2 driving grippers to brace itself in the rock. A drilling stroke is 1.2 meters long and normally takes about 30 minutes. In the so-called driving shield, After the drilling stroke, driving operations stop. The trailing hydraulics then advance the gripper shield. Once the grippers are retightened, the machine resumes driving operations. After the drilling stroke, the TBM has been extended as far as possible. Before driving operations resume, it's necessary for the entire rest of the machine to be drawn forward. The remainder of the TBM consists of 7 trailing units with the technical equipment to supply the machine. And at Marty's request, a redundantly designed fallback prevention device for optimum safety. This device prevents the machine from sliding backward down the sloped shaft and primarily consists of 2 pairs of fallback grippers. Using extremely powerful hydraulics, the rear pair of grippers can be moved on the machine by about the length of a drilling stroke. The grippers are seated on connecting rods and are spread by hydraulics. If the grippers are in the rock and the machine wants to move backward, the grippers automatically tighten in the rock due to the sloped connecting rods, halting the machine. The self-inhibitory mechanism operates solely on the basis of its geometry, functioning even in the event of an accident and loss of power on all hydraulics on the TBM. In the event of total loss of power while a pair of grippers are retracted to move the machine, these hydraulics would be automatically ejected by emergency tanks with highly compressed nitrogen, causing the self-inhibitory mechanism to be triggered on this pair of grippers as well. This means that the machine is secured by both fallback grippers even in the event of a total failure. Only the gripper in the gripper shield would lose its holding force, as it does not have a self-inhibitory mechanism and needs to be actively pressed into the rock to be fixed in place. Let's now return to the locomotion of the TBM. After the TBM reaches its point of maximum extension during drilling, the front fallback gripper is retracted. Then the rear gripper, which is fixed in place in the rock, is slid backward and the machine is pushed forward. Now the front gripper is fixed in place and the rear one is drawn forward. Once both fallback grippers are securely fixed in place in the rock, the gripper shield is released and advanced. Then the rear part of the machine is brought forward again. The machine is now in the position of minimum extension. Driving operations begin again. Drill. Advance the gripper shield. Drill. Draw the machine forward. Advance the gripper shield. Draw the machine forward. And drill again. On the basis of this locomotive cycle, the machine advances through the solid rock in 1.2 meter increments. On its steep path to the slide chamber 800 meters above, it's continuously fixed in place in the rock using 3 pairs of grippers during drilling and at least 2 pairs of grippers during locomotion. Let's move on to the slide chamber. Like the access tunnel, it was constructed using the blasting method. As with the access tunnel, the conditions were not always completely dry. Oh well, but all joking aside, the explosive charges were reduced to protect the nearby retaining wall from vibrations. Nevertheless, the blasts are impressive. The entire construction site must be supplied via the 38-meter deep access shaft. Managing the site logistics with a material cableway is extremely complex. All construction equipment in use must fit through the shaft. That's why the shaft is oval in shape and has such a large diameter. In the slide chamber, the power plant's works water system can later be shut down for maintenance purposes. The pressure gallery opens out at the wall on the southern end of the cavern. The arrival niche for the tunnel boring machine was already created. On the other side of the cavern, the 140-meter-long headwater gallery to Lago Ritom is driven. The concrete finally reaches its place of installation here, conveyed from the slide chamber by a concrete pump. Fresh from the valley and still warm, steam arises from it in the cold mountain air. The headwater gallery is driven to within 20 meters of the lake. The last part of the gallery can be constructed only in winter, when the lake receives very little inflow and can be lowered to below the gallery. Another gallery is being built for draining the cavern, and later also for maintenance purposes. During construction of the slide chamber, the tunnel boring machine Let's see how far they've come so far. The peak speed at which we are flying around this animation is 600 kilometers per hour. The TBM has progressed much more slowly than that. In 4 months, it has traversed 450 meters of rock and about 200 meters of altitude. It can be reached from the launch cavern via a tunnel railway. In the shaft, the alpine water entering the site runs down, and the washed-out excavation material is in the material channel. This means there's a risk of falling rocks, but the train cabin offers protection. On the tunnel wall there are pipes for supply water, wastewater and compressed air, and on the other side, fresh air and electricity. The ride can take up to 20 minutes. There's time here to relax, to chat a bit, or to discuss the situation. Finally, they reach the tunnel boring machine, this 3-meter thick worm chewing its way through the rock. From here, they continue toward the drill head, taking the stairs over the trailing units. At 3.2 meters in diameter, the TBM is very narrow, and the existing profile is perfectly utilized. The pipes of the fresh air supply and the shaft for the excavated material hang under the machine. The supporting structure and the stairs for the operating crew are above it. A material cableway is routed over all trailing units. The profile for the cableway must be kept clear on all trailing units. Space is extremely tight, and only what is absolutely necessary is kept on board the TBM, of course. There's a dust lock and an 11 kilowatt drilling rig on trailing unit 1, directly behind the fallback prevention device. The ridge vault is secured here with rock nails and steel grids to protect the downstream work. Trailing Unit 2 carries the indispensable air dedusting system and a shotcrete pump. Trailing Unit 3 is for the TBM control station and the hydraulic oil pressure pump with oil tanks. On the other trailing units, there are transformers, control cabinets and electronics. Hose reels for the water and compressed air supply, water pumps, the fresh air supply and the tunnel rail station. The track for the tunnel railway and the material channel are periodically extended through an assembly opening in trailing Unit 6. There's virtually no storage space on the entire TBM, and everything needed arrives from the launch cavern just in time. Here, everything required is prepared and delivered for direct use on the TBM. It's necessary to perfectly coordinate all transport operations because installation of the track segment blocks the cableway and all other material deliveries. The material channel is extended between the rails. The trailing units must be moved along and the men are working at full tilt. The fallback prevention device then takes another step through the mountain. Travel of 1.2 meters takes about 2 minutes. When the front gripper is fixed in place again, the rear one is drawn forward. The machine is then ready for the next drilling stroke. In parallel with the work on the mountain, Marty constructed the new power plant control center in the valley. Inside the building, up to 8 cubic meters of water per second will pass through each of the 2 turbines. To withstand the extreme pressure of the water standing 800 meters high in the sloped shaft, the turbines and supply lines are cast completely in concrete. During subsequent operation, the turbines are switched on and off again on short notice, depending on demand and the current price of electricity. In order to prevent constantly fluctuating levels in the Ticino, a 100,000 cubic meter compensating basin was built. With the power generated by the water flowing into this basin, it's possible to comfortably bypass the critical choke point of the Gotthard traffic jam by taking the express train under the Gotthard Massif. But all that is a long way off, as there is a problem inside the mountain. The TBM has come to a standstill some 300 meters below the surface. The reason was material balance. The TBM had delivered 12 cubic meters of excavated material without making any progress. The material must have slipped in from above. It was an alarming situation. Once extensive cavities form above the TBM, it's no longer possible to get a handle on the problem. The entire entire project was again in jeopardy. 6 exploratory and injection bores were drilled from the drill head to investigate the site and prepare for countermeasures. Upon evaluation of the rock hardnesses determined by the drilling, the following became clear. Between 2 solid rock sections moving against each other, a stratum of broken rock that was completely crushed in some places had formed, known as fault gouge. For the sake of clarity, the transition zone between hard and soft rock is shown transparently here. The geologists concluded that an area measuring a bit more than 20 cubic meters had started to shift in the loose rock, loosening and releasing some of its mass to the TBM. In order to prevent more rock slides during further driving operations, hollow steel rods known as spiles were inserted into the boreholes. Cement was then injected under high pressure through the spiles and from the beginning of the holes. The spiles remained in the rock, serving as reinforcing steel. The ridge area was reinforced, followed by the side areas. All boreholes were driven until load-bearing rock was reached again. Then, after 4 weeks of injections and around 13 tons of injected cement, the moment of truth. With the machine stationary, the cutting wheel was carefully turned on again. To the great relief of the tunnelers, there were no further rock slides. Now in the unprotected area directly behind the drill head, which is the TBM's most dangerous location, the tunnel vault was reinforced by steel segment rings. This was to protect the miners, but above all to provide a solid foothold for the downstream grippers, which would not have been able to grip reliably in the fault-ridden rock. Then they could finally pass through the fault zone while exercising extreme care. As they did so, 25 centimeters of tunnel were driven and another ring was installed periodically. During the driving operations, areas of fractured rock came to light. Even solid-seeming rock can be completely crushed. Above the machine are about 100 tons of broken material that have already shifted, and you can see the stress of the situation on the tunnelers' faces. During driving operations, installation of the next ring is already being prepared. To the greatest extent possible, loose rock fragments are removed and crushed for removal in the material channel. New ring segments called liner plates are passed through the grinding channel underneath the fallback prevention device and then brought to the installation location using a cable hoist. Such mechanical work aids were installed wherever possible on the TBM, but installation of the liner plates cannot be mechanized and is hard manual labor. A total of 85 meters of liner plates and thus over 100 tons of steel were installed in 6 fault zones and backfilled with another 100 tons of concrete, a great achievement by the tunnelers. In the gripper area, the liner plates are welded in addition to the bolted connection. Then the ring is installed, but the effort is rewarded with just 25 centimeters of driving operations. Once the driving presses are fully ejected, the gripper shield is drawn forward. When the liner plates enter, the gripper shield and the fallback prevention device are kept precisely level through adjustment of their movable sliding shoes. The driving shield, gripper shield, and fallback prevention device must always remain precisely centered in the drilling axis. Otherwise, the TBM would become wedged and jammed in the shaft due to the major compressive forces during driving operations. In the worst-case scenario, the machine would be severely damaged. There's a lot to consider when making your way through a mountain, and operating errors can have dire consequences. Controlling the TBM requires experience, knowledge, and intuition, making it a task to be left to absolute experts. Thanks to this expertise and the measures developed by Marty, it was possible to pass through the massive fault zone within a month. Only the fallback grippers don't fit through the liner plates, so adjustable wedges are used to reduce the width of the fallback prevention device. Then it's finally possible to get past the fault zone. In the solid rock encountered at this point, the driving operations are progressing well at about 20 meters per day. However, the next challenge already lies ahead, because making it through the inflection point is difficult for the fallback prevention device, as the components always need to be precisely aligned with each other, but the grippers that are fixed in place cannot rotate or move in the rock. Then the turn is made, and the machine is actually at a slope of 42 degrees. It's only held in place by its tiny-looking grippers. Wherever the rock isn't 100% reliable, liner plates are placed for absolutely secure seating. The machine has crushed about 5,000 cubic meters of rock so far. The roller cutters still look like new in the animation, but this is no longer the case in reality. It's high time to change the cutters. Muscle power is once again in demand. The background music may sound like easy listening, but the work is very hard, with each cutter weighing 80 kilograms. With dozens of cutter changes, the sequence is cable weigh, grinding channel under the fallback prevention device, the auxiliary cable way to the cutting wheel, then bolt on the locking mechanisms, briefly test them, leave nothing behind in the cutting wheel, and it's ready to go. Excavation material is again sliding out of the wheel. Incidentally, after it takes a slide in the launch cabin, the material is dewatered by a sifting machine built by Marty subsidiary Simatec and transported away. Together with the material from the compensation basin, it's transported to the landfill by a Marty Technic belt conveyor, sorted by a pivotable belt, and ultimately transported away by rail. So far, so good. If only they weren't always encountering these problems in the mountain. So, back to the dramatic music. What happened? There's a discussion taking place in the drill head because the TBM has again driven into a fault gouge stratum, and this time there was a cave-in. This is what it should look like in front of a roller cutter, but this is what it actually looks like. And in front of the upper part of the cutting wheel, there's something that shouldn't be there at all. A cavity. The only good thing about the situation is that the fault zone is thin. Through the cutting wheel you can already see the solid rock, here on the right, where the fault gouge, here on the left, has slipped. Because of the thinness of the fault zone, Marty decided to attempt a daring experiment after precisely measuring the cave-in. Through the cutting wheel, a vault is created. Several cubic meters of shotcrete need to be injected at various wheel positions. The de-dusting system is running at full tilt, but soon nothing can be seen in the cutting wheel, and the work is interrupted. The dust lock in the trailing units is closed, of course, facilitating material delivery to the shotcrete pump. To continue the concrete work, the cutting wheel is turned a bit further, and debris again rains down into the machine. So shotcrete is again injected until no more material comes down when the cutting wheel is turned. Then the machine is driven forward 25 centimeters with extreme care. A ring of liner plates behind the drill head, and again from the beginning. The attempted experiment, which was quite daring in view of the extent of the fault zone, was successful, making it possible to cross the zone without injection drilling and saving a good 5 weeks in the process. As it turned out, this meant that the last truly critical area of rock had been overcome. Although the machine was now approaching the surface again, and difficult rock was predicted, there were no further problem zones. And so after the machine made its way through 1,400 meters of the mountain, overcoming 800 meters of altitude along the way, the moment that sometimes seemed impossible finally arrived on February 23rd, 2022. I'm now looking forward to experiencing the breakthrough with you and finally being able to say, let's celebrate together. The primary reason for our success is our experienced crew. My very special thanks to you. After the first toast, the tunnelers retire to the official festivities in the valley with a final flourish. The cutting wheel Halfway through the rock, the machine arrives back in the launch cabin. The fallback prevention device has done its job perfectly, and the tunneler's last trip with the device takes them out of the tunnel and into daylight. Some 800 meters above, the final section of the headwater gallery to the side chamber is being built from the drain at Largo Riton. This will complete the tunnel system of the new pump storage plant. The power plant is scheduled to be done in 2 years, and there's still a lot to do before the water flows from there to the turbines. However, the story of the tunneling crew ends here. The shell construction of the new Riton pump storage plant was a complex challenge. Based on creative cooperation, the companies of the Marti Group successfully overcame complex problems and unexpected difficulties. We are proud of this accomplishment.